So I was thinking that for this morning, we would see if there were any practice homework quiz questions. And then I wanted to go over the notes that I posted this morning about statistics and data distributions. So does that work for everybody?
Yeah, that sounds good.
Yes.
Okay, great.
Can we maybe do like a couple of like the homework quiz questions and then the notes, obviously, like you said. So
Yeah, so this was the order I was thinking. Is that what you're thinking?
yeah.
Okay, great. So what do we have questions about?
I was thinking like 16 probably.
Okay.
I think, well, let me see.
16.
Yeah, 16, and then I don't.
Okay, so 16 says, how many license plates are possible if there are 6 backgrounds to choose from? Three letters. So we've got 1, 2, 3 letters. Oh, that looks like a 6. That looks illegible now. Okay, great. And 4 numbers. So 1, 2, 3, 4, and these are numbers. Okay, and then it said, assume that the letters can be repeated. So this is going to be like A to Z. So there's 26 letters in our alphabet, and these can be repeated. And then there's numbers, but the numbers can't be. So that means I've got 10 choices for the first number I choose, but then I only have 9 because I've already used a number and I can't repeat it. So then my third choice here would be 8 because I've used 2 numbers already, and then 7. So I'm using the fundamental counting principle here. It's going to be 6 times 26 times 26 times 26. So for the backgrounds, and then for the letters that we can reuse, and then 10 times 9 times 8 times 7 for the 4 numbers that we can't repeat.
Okay, so you just use the fundamental accounting principle here.
Exactly. So then you just multiply that out.
Okay.
Does that make sense?
Yeah.
So
this isn't is this kind of like a permutation, or is this just
so
like the outcomes, or like counting across?
So technically we are counting like different orders because each license plate would be distinct, right? But when we use the NPR formula, when we use the NPR formula, we actually we have a total of 17, okay, like 17 things. So we've got 17 things, right? But then we're only choosing some of those 17 things. So I guess if we've got 6 permute 1 background, right? And then we've got times 26 permute 1 times, like, I just don't, like, it's possible this method would get us the same answer, but it's certainly not the fastest way to get the answer, because we would still have to multiply all of these things out. So I think that 6P1 turns out just to be 6. Yeah.
Oh, so that's why you multiply 6 times 26 times 26, because
exactly. Because even if we did,
it doesn't affect it. Since it's only 1.
Even if we used it as a permutation, we'd still end up with this.
Yeah. Okay. That makes sense.
All right, cool.
Okay, cool.
All right. Do we have any other questions from the practice homework quiz?
Could we do maybe like 13?
Mm-hmm. So 13.
Yeah.
Given a standard deck of 52 cards, what is the probability of drawing 2 red cards? Okay, so there are 26 red cards in the deck because 13 for the hearts and 13 for the diamonds.
Mm-hmm.
And we have to choose 2 of them. The order doesn't matter. It only matters that they're red. And we're comparing that to a full deck with all 4 suits, 2 of the black suits and 2 of the red suits. And we're choosing 2. And what does this give us? So in my calculator, I'll put in 26, choose 2, divided by 52, choose 2, and I get roughly a quarter. So this,
Yeah, I'm kind of a little bit confused on that. So like, why isn't it just like 26 over like 52? Because I get the 26 over 52, but why are you is it because you're choosing them or?
yeah.
Okay.
Does that, well, I mean, so think about it. If you shuffle a deck of cards and you choose 2 cards, what's the probability that they'll both be red? It shouldn't be 1/2 because you don't know the order that the cards are in the deck, right? It's not, when you shuffle, you've got a mixture of red and black.
Oh, okay, yeah, that makes sense. So
right?
That's why
so if I shuffle and then I just draw 2 cards, it shouldn't be 1/2.
Yeah.
Because I don't know how the cards are ordered in the deck.
Mm-hmm.
Does that make more sense?
Yeah, that makes more sense. Okay.
Yeah.
And then you're just doing it as, well, you could do it as it'd be as a fraction, right?
Yeah, but like, yeah. So you totally could, but my calculator just gives it to me as a decimal. But I guess it's a little bit less than 1/2 times 1/2, right?
Yeah.
Because the first card there, it's either red or it's black. And the second card, it's either red or it's black. And so that would be 1/4. So it's just a little bit less than that because we're choosing 52, out of 52 cards. Maybe there's, red, black, red. Maybe it's, it's just more random.
Yeah, that makes sense because it's shuffled instead of like having like, because
right.
there's so many different options like 52.
Exactly.
So theoretically speaking, if we were to do like you draw 1 red and 1 black, would it be the same probability or would it be different?
Well, so that should be, okay. So I think that would be different. So if we want to know the probability of 1 red and 1 black, the probability of drawing 1 red would be 13 choose 1 out of 52 choose 1 times 13 choose 1 out of 52 choose 1. I think that would be even smaller. Does that make sense?
Yeah.
Yeah, so the choose 1, it doesn't really affect it. So you just multiply 13 by times 13 and 52 times 52, right?
Yes.
Okay, that makes sense. So
Is that good?
Yeah.
Okay, anything else from the homework quiz? The practice homework quiz? That's all good? Or you want more time?
Hey, Miss Nevis, so Krista texted you our group. We don't have to text you as well, do we?
Nope, I got you.
Okay. All right, thank you.
I'm making a list so I can, I don't know why. So I can account for everybody, I guess.
Okay.
Okay, so are we ready for notes?
I think so, yeah.
Okay. All right, so the notes have 4 pages because there's a lot of diagrams. So I numbered the pages up here. Okay, so this is statistics and data distributions. And the first example is the Algebra 1 review. And then we'll look at stuff from section 11.1. So the essential questions are, what is mu and sigma? And what do they indicate? So remember in chapter 8, we used a sigma that looked like a capital E. This is the lowercase version of that letter. So when you see the uppercase letter, that means summation. When you see the lowercase sigma, that means standard deviation. So question 44 says, in a normal distribution, what % of data lies within 1, 2, or 3 standard deviations of the mean? And 44 says, how do I calculate a z-score and use a standard normal table to find a probability? So that's what we'll be talking about. So the mean mu is the average of a numerical data with values x1, x2, x3, all the way up to xn, and is found by adding the values together and dividing by n. So that's just a typical average. The standard deviation sigma is a metric of how a typical value differs from the mean mu and is found using this formula. So we take each data set and subtract the mean from it. We square that, we add all of those values together, divide it by the number of values in the data set, and then take the square root of that. So that's how that one works. So that should be, you should have seen that in Algebra 1, but that was 2 years ago, so it bears repeating. Now, a histogram is a bar graph that shows the frequency of data values in intervals of the same size. So jumping ahead, you can see this is a bar graph, and you can see the intervals here all have the same width of 5 values. 0 to 4 is 5, 5 to 9 is also 5, all that. Okay, so here's our Algebra 1 review problem, just so we can talk about what the mean and the standard deviation are, because we'll need it for the Algebra 2 portion. So class scores for a test are 3, 8, 12, 14, 15, 2 people got 19, somebody got a 20, 3 people got 23, somebody got a 25, and 2 people got 26s. So our job is to find the mean and standard deviation in part A, and part B says to draw the histogram and interpret it. So in part A, I noticed that there are 15 scores when I count all of these up, and so n equals 15. So when I'm finding mu, the average, I add up all of the values and I divide by 15, and that gives me approximately 18.1. Is that part okay?
Yeah, that part makes sense.
All right. So then to find the standard deviation sigma, I put in the test score values, I subtract the mean from them, I square all of those to make sure that they'll be positive, and then I divide by 15, and then I take the square root. So this is kind of the distance formula and the average combined. So that's why they say it's the typical difference, right? Does that make sense?
Yeah, kind of. I get like the formula and how like you need to find the mean first to find the
to be able to do the standard deviation, right?
On the lower equation, is that a square root or is that a bracket around it?
So there's a bracket here for just the numerator, and then dividing by 15, and then all of that is in the square.
Okay.
Yeah, so when you do the standard deviation, you have to really be focused and no distractions, because it is annoying to put all of this in and then get a syntax error because you forgot to close a parentheses.
Oh, yeah.
So just
so like you have to, and so obviously you do the numerator first in the calculator, right?
right.
You have to do all the parentheses and stuff correctly.
Right.
It'll take a long time, and then after you get that, you divide by 15, and then you square root.
Yes.
Okay.
So it's a little bit time consuming.
Mm-hmm.
Okay, so I found the standard deviation to be like 6.6. So in part B, we were asked to draw the histogram and then interpret it. So this is the number of people that received the scores in each bandwidth. So I've got one person that got 3, and that's between 0 and 4. I've got one person that got an 8, between 5 and 9. I've got 2 people that got between 10 and 14. That's a score of 12 and a score of 14. I had 4 people that got 15 and 19. So 2 people got 15, 2 people got 19. So does this make sense? You can see how the histogram works?
Yeah, so this is just on the mean, right?
this is just on these scores. Like I'm just organizing these scores into a
Okay.
histogram so that I can see what really happened there. I mean, and this standard deviation is pretty significant for a test that had a maximum of 26 points.
Hmm.
Do you follow what I'm saying there?
Yeah, so wait, so that's like why is so 6.6? So this only goes up to 4, but this doesn't affect like the deviation, right?
So
Like,
so the standard deviation tells us that if there was a typical score,
hmm,
well, hold on, I'll come back to that in a second.
okay.
This is just saying the number of people that got scores in these ranges.
Okay. Yeah.
Does that make sense?
Yeah.
Okay. All right. So part of this, part B, was to interpret the histogram. So that brings us to our second page of notes, which I've given you. This is page 2, and I've given you the this diagram. So this is a normal curve, a normal data distribution. This particular curve is skewed right because the tail is on the right side. So if we interpret this in the example that we have, this means that a lot of people would have done poorly and just a couple of people would have gotten higher scores. This means that the middle score was the average. Majority people got the average, and some people didn't do well, and a same amount of people that didn't do well did better than the average.
That makes sense. So that's like more for like kind of like tests, I guess, or like.
Right. Yeah. So when we have numerical data, this works out really well.
Mhm.
Whether it's test scores, or we've got an example with the weight of newborn infants, things like that.
Okay.
Okay. So then this happens to be where more people did well, and then some people got lower scores. So this is skewed left because the tail is on the left side.
Wait, so this one is where like more people got worse scores for the left one, or
This one. Like if we're assuming these are the lower scores on this side,
Mhm.
and that the horizontal axis would be increasing.
Mhm.
So skewed right means more people got low scores, and a few.
Oh, because on the left it's like still going up since there's a lot of people that got like, let's say, was like 3 or 4,
Exactly.
right? Okay, that makes sense.
Right. So here, this is more people did well and a few people got low scores.
Yeah. Okay.
Which is basically what happened in our histogram, right? So this one we would say that this is skewed left because the tail is on the left side.
Yeah. Okay.
Does that make sense?
Mm-hmm.
Okay. So algebra 1, yeah, here's the answer to that, where we said our histogram is skewed left because the tail of lower scores is on the left. So what we've been saying. Here's our next illustration. So this is a normal distribution. So the mean here is in the center, and this is +1 standard deviation, +2 standard deviations, +3 standard deviations, and this is the mean -1 standard deviation, -2, -3. So notice within 1 standard deviation, we have 68% of scores, right? So 34% of the area under this curve is right here, and this is the other 34%.
Okay. So that's like 40, obviously, since it's higher up.
Exactly. So then within 2 standard deviations, we'll have 95%, which means this is 13.5% of the area under the curve, and so is this. And then within 3 standard deviations, we have 99.7% of the data. So that gives us a 2.35 and a 2.35% here, and then this is 0.15%, 0.15%. Does that make sense?
Mm-hmm.
Okay, so what I need you to do is I need you to memorize these values and where they go. So it's really like 4 values because they repeat on the other side.
Okay, well, will this happen like with every single normal distribution?
Yes,
Like every single one of
that's
this?
the power of it. If you have data that's normally distributed, then you can count on these values.
Mm-hmm.
Right. So in our example, we didn't have data that was normally distributed. We had data that was skewed left.
Uh-huh.
So what we had in our example does not apply here.
Okay, that makes sense.
If something is normally distributed, you can use these numbers.
Okay.
Okay, so that's page 2. Here's page 3. And this is example 1 from our textbook. So it says a normal distribution curve has mean mu and standard deviation sigma. Find the probability that a randomly selected data value x is less than or equal to a mu plus 2 sigma. So here's what we're trying to find. I drew a sketch. Maybe I'll put some of these on Edmodo for you guys because I don't know. My undiagnosed OCD is kind of off the charts with this little drawing here. But anyways, so I'm looking for the area under the curve up to here. So all of the area that I've shaded. So this is 0.15 for this tiny tail over here. This is 2.35. This is the 13.5, 34%. We've got another 34% and a 13.5. So I added up all of those areas and I got 97.5%. So it's pretty likely that if I randomly choose a data value from my set that's normally distributed and I want something that's in this area of the curve, I've got a 97.5% chance of.
Okay, so you're not including the what is it, like all the way to the right? That's not included since that's greater than.
Exactly.
X.
Exactly.
Okay. If it was like x is like greater than m plus 20, then it would
Okay,
just.
so this is mu plus 2 sigma.
Oh, sorry, mu plus. If it was probability of x is greater than mu plus 2 sigma, it would just be the white.
Yeah, so it's also possible, like we could have something where it was a probability that mu minus sigma is less than or equal to x is less than or equal to mu plus 3 sigma. You could also find that. Does that make sense?
Yeah.
So then that would be what? So mu minus sigma would be 34 plus 34 plus 13.5 plus 2.35 plus 0.15. And you just add all of those up.
Okay, that kind of makes sense. So you're not including the things on the left since it's less than or equal to x.
Right. So these are the boundary lines that we need.
Okay.
Okay. Other questions, or are we all set?
I think we're good.
Okay. So example 2 from our textbook says the scores for a police academy graduation test are normally distributed with mu equals 55 and standard deviation equals 12, or sigma equals 12. The scores range from 0 to 100. What percentage of graduates have scores between 31 and 55? And then part B, what percentage of graduates will have a 79 or higher? So again, I sketched the curve and I put the values in. So the mean is 55, according to what they told me. 55 plus sigma of 12 is 67. So now we're at mean plus 2 standard deviations would be the mean plus 24, which is 79. And then the third standard deviation is 91.
Okay, so you're adding by 12 on the right, positive, and then you're subtracting 12 so that it'll, right, since it's the normal deviation.
Yeah, exactly. So I put the mean in the middle. I add 12s up this way, and I subtract 12s this way.
Okay.
So that I have the boundary lines.
Yeah.
Okay, so then part A says the probability that x is between 31 and 55. And so that's going to be this area under the curve over here. So this stuff. And that happens to be 13.5 and 34%. So I added those to get 47.5% of the police academy test scores are going to be in that range. And then the probability that they'll be greater than 79 is from here, is just this area right here, right? So that's 2.35% and 0.15%, which gives me 2.5%.
Okay, so like let's say it was just x is greater than 79, then it would kind of be like you couldn't really tell because that it's not including it. So then the percentage will be like off, right?
Yes, but I can help you with there's a thing for that. There's already a fix for that.
Oh, okay.
So are we confident with this example?
Yeah.
Okay, and
Yeah,
then,
I think it makes sense.
okay, so how do we feel about those scores? Like if these are not made up scores, that's a little bit concerning.
Yeah, they should probably study more. I guess.
Yeah.
Yeah, or where something's not working. Okay, so here is our page 4, and I've got one example on this page. So example 3 says, a study finds newborn weights are normally distributed with mu equals 3,270 grams and sigma, the standard deviation, is 600 grams. What is the probability that a randomly chosen infant weighs at least 2,790 grams? So again, we want to sketch the normal curve and then put in the values. So mu, they told us, was 3,270. They told us mu minus sigma should be 2,670. And they asked us about 2,790. Notice that's not on the boundary line, right? It's in between. So we can't use the strategy that we were using.
So which was the percentage, right?
Exactly. So instead, we have to use a standard normal distribution. So this is how it works. A standard normal distribution is a normal distribution with mu equals 0 and sigma equals 1. To translate an x value from a normal distribution to a standard normal distribution score, we'll use this formula, and you probably want to highlight that. Okay, so the new score is called the z-score. So we're going to take this to something that looks like this is mu plus 1, this would be mu plus 2, this would be mu minus 1, this would be mu minus 2, and my graph is too narrow, so that's as far as I'm going to get. We'll say dot, 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 dot. Okay, so that's what we're turning it into. Okay, is that part okay?
Mm-hmm. Wait, so like if it's between the boundary instead of like, or yeah, if it's not on the boundary in between, then you're gonna always use the normal distribution formula.
Yeah, we have to use the standard normal distribution.
Or standard, yeah, sorry, okay.
Yeah, does that make sense?
Mm-hmm.
Yeah. Yeah, that makes sense.
Okay, all right, so also notice that our question is saying at least. So we want this area over here. So that's an important detail. So an infant that weighs at least this amount, we're looking for this over here, not this over here, because that would be less than, if this is the bottom, then we want this.
We're including 2,790, right?
Right. Okay, so you can see I've added, notice this weight isn't one of the boundary lines, so we need to calculate the z-score. So using the formula, we've got the value that we're looking for, the 2,790, minus the mean of 3,270, divided by the standard deviation, 600. When I plug this into my calculator, I get this number, negative 0.8. Is that okay?
Yeah. Could we maybe do like another example of this? Because I feel like this is kind of like the...
Yeah, for sure.
Okay.
For sure. Okay, so now this is the z-score, and this is the table of z-scores. You do not have to memorize this. You just have to know how to use it. On homework and tests, if we do another homework quiz or whatever, I will give you this. So you'll have it. Does that make sense?
Yeah.
Okay. All right, so this number to the left of the decimal place, we find on the left column. The number to the right of the decimal place will be on the top row. We want where they intersect, which is here.
Okay, that makes sense. So the left is...
The negative 0 is here.
Okay.
And then we just follow this over to the 0.8, and I get this value.
Okay, that makes sense.
Okay. Now, the standard normal table gives me the percentage of the area to the left over here. So this is the 0.2119. Our particular question is asking about here. So we need to use the complement to find that.
Okay.
Should I repeat that?
Wait, so the 0.2119 is to the left, and we want to find the right. Or we want to find 2,790, and then that including into the right. So we just do minus.
Mm-hmm.
That kind of makes sense.
0.02119. Is that okay?
Yeah.
Yeah.
All right. Anybody want me to repeat that? Okay. All right. Seems like we're confident with that. So I use I'm using the complement here. So 1 minus the probability that x is to the left of the value we're looking for. And to the left of the value we're looking for from the table is 0.2119. And when I subtract this, I get 0.7881 or 78.81%, which seems a reasonable estimate for this area under the curve over here. Do you agree with that?
Yeah.
That's how it works. That's how we use that. So my note is just saying that the standard normal table represents the area under the curve and to the left of the boundary line. So we have to use the complement. So that's why I'm using the complement here.
So if we do another question on this, it'll always happen. So so you'd always have to find the complement, right?
Well, no. So it's totally possible. Okay, so what if we use the same data, but we want to find the probability that a randomly chosen infant, let's see, weighs, I don't know, the probability that a randomly chosen infant weighs less than, I don't know, let me make up a number. Uh, 2,730 grams.
Okay.
So we're looking for
Everything to the left.
yeah. Does that make sense? So we know that that won't be, I mean, I've specifically chosen that number, so it's not 600. So we're looking for the z-score, which is x minus mu over sigma. And so that's 2730 minus 3270 over 600. Negative 0.9 is what I got. So negative 0.9 would be here. So we've got 0.1841. So that's the answer. So the probability that the x is less than 2,730 grams equals 0.1841 or 18.41%. Does that make sense, or did that make it worse?
Oh, that kind of makes sense, but I'm just I'm still a little bit confused, but I kind of understand what you're doing. So this is the so this is everything to the left, and to the right we already found, right? So
well, no, it's just because this example I just made up says less than.
Mm-hmm.
The other example says weighs at least. So
yeah.
If it weighs less than, that's going to be weights over here, right?
Yeah.
So that's exactly what these numbers are. If it says weighs at least, then that's values over here.
Yeah.
So the complement to these numbers.
Oh, okay. So the complement to to, or greater than or equal to the 2,790 grams, which is 78.81%, is 18.41.
Right. Right. So that's kind of why we want to draw the picture, because this seems like, yeah, that could be like 22%. I get that. And so this is like 78%. Yeah, that makes sense.
Mm-hmm.
Is that okay?
Yeah.
He says hesitantly. Other questions? Other things I should clarify?
I think we're good, but can we like do another question?
Yeah, let me
Okay.
open our book and find one. Do you want another question like this one?
Yeah, it's similar to like this one, I think.
Okay. So let's see here. Okay, so here's the question. Okay, so it says, a busy time to visit a bank is during its Friday evening rush hours. So this is old, now everybody banks online, it's no problem. For these hours, the wait times at a drive-through window are normally distributed with a mean of 8 minutes and a standard deviation of 2 minutes. You have no more than 11 minutes to do your banking and still make it to your meeting on time. So we have X is less than or equal to 11 minutes. Because you have no more than 11 minutes. Does that make sense? That it's 11, less than or equal to 11 minutes. What is the probability that you will be late for this meeting? So the probability that it will be X is greater than 11 minutes. Right? That's what they're asking us?
Mm-hmm.
Okay, so this is 8, this is 10, this is 12, and so 11 minutes is right here. So we know we need to use the z-score. So z equals x minus mu over sigma, which is 11 minus 8 over, we said 2, which is 3 over 2, or 1.5. Okay. All right, so remember this is greater than. So for the z-score, 1.5 is right here, 0.9332. So the probability that x is greater than 11 will be 1 minus this number. I just had it in my 1.5, 0.9332. Does that make sense? Because the 0.9932 represents all of this. And we want to know what are the chances you're going to be late? Oh, sorry. So the 0.9332 represents all this area.
Mm-hmm.
And so we want to know, so that's why I'm using the complement again.
Okay. Like,
Because
so like whenever, so I was trying to say on like on the last one, so like whenever you're finding like the first, like whenever you're trying to find like whatever's to like right or like or left, then you want to find the complement because then that it relates to like the like,
so the area, the numbers in the table are to the left. So if you want something to the right of it, then you have to use the complement.
okay. Wait, because is it because it's negative? Is that why? Or
What's negative?
like you see it says -0 and then it has all the like in the last problem. That's why you wanted to find the
Well, yeah,
complement.
so these are the standard deviations to the left, right?
Mhm.
Because it's, right, so it's mu and then -1, -2, -3.
Huh.
So it would be negative on this side
Yeah.
and then positive on this side.
Mm-hmm.
So that's why this number is really small and this number's bigger.
Mm-hmm. Yeah.
This number's the biggest, right? Because 3.9 is like, does that make sense?
Yeah. That's why you want to find the complement.
Right, right. Okay, so are we feeling more confident about that?
Mm-hmm.
Yeah.
Okay. So, but it wouldn't hurt your feelings if I put a lot of explanation in the answers for this homework set?
That's fine.
Yeah, okay. Okay. All right, do we have any other math questions?
I don't think so. I think we should be good.
Okay, so I'll pause the recording.